on to the second question. So I'm going to go ahead and quit my kernel. I'm going to go ahead and do a separate section for number 2, and then let's go ahead and get started. So no pressure, just DFT. So we're looking at some of these thin-walled pressure vessel thin-walled pressure vessel hoop stress measurements of a biological capsid passes through this extracellular matrix, and we get the following signal as function time. So we need to figure out lowest dominant maximum frequency, and let's just go ahead and calculate all the values we see. So clearly the signal appears to be periodic. The question is, where is my period? So I see it go down, up, flat, down, here, and then I repeat that whole down, up, down, this, down, here. So the period is 1, 2, 3, 4, 5, 6, and then it repeats there. So if I translated this, and let's go ahead and actually go down here. So go here, so 1, 2, 3, 4, 5, 6, and then actually let's go ahead and count 1, 2, 3, 4, 5, 6, and then it goes again. So that's my period here. So my period is going to be that 6 intervals, or 6. Actually, my number of points is going to be equal to 6. My delta t in this problem is going to be equal to 0.01. So I know that my delta f is equal to 1 over delta t. Actually, 1 over my period. So my period t is equal to n times delta t. So let's go ahead and let's kind of start giving these values in Mathematica. So let's go ahead. My n equals 6. Actually, let me zoom in a little bit when we're defining some values. It'd be nicer to see. So my big N equals 6. So my delta t is equal to 0.01. My f sub s, excuse me. So my f sub s is equal to 1 divided by delta t. I know that my delta f is going to be 1 over my period. I know that my delta f is also equal to 1 over n delta t. And we know that we could also rewrite that as basically f sub s over n. And we also know that my f Nyquist is going to be equal to, kind of, again, those number of harmonics, we go to n divided by 2. Delta f is equal to my f Nyquist. And we should also know that that is going to be, if we know that our delta f is equal to 1 over n times delta t. So we know that that is that, and then so we know this is also equal to f sub s over n. So we can kind of rearrange it. So we know that f sub s is equal to n delta f. So we also know that our f Nyquist is equal to f sub s over 2. So just some quick values you could kind of, again, we all know this from basically our from all our numerous lecture notes, and then also from some examples in P-sets. So let's go ahead and kind of factor it out a little bit nicer. So big N times delta T, f sub s. Actually, we don't want to suppress any of these outputs. Actually, I'm going to go ahead and put them all in separate lines. So I'm just going to do a little bit of reformatting. So let's just do them all in separate lines. So my big N is equal to 6. Usually I'll definitely not kind of format my code in this way, but for ease of keeping track, delta t is equal to 0.01. Let's make sure that that's the case. Yep, 0.01. So that's the value here. And then I can now do my t is equal to, now again, that's why you need to clear your notebook, delta t, and double check it with just some math as well. F sub s is equal to 1 divided by delta t. So my f Nyquist equals f sub s divided by 2, which we derived over here, right there. And we also know what the Nyquist frequency is as well. So, oops, let me put that away. So, Nyquist frequency, what else can we calculate here? My delta f equals 1 divided by t. And we can kind of confirm that, not that one. We can confirm this with our kind of other suspicion, right? So we also have that expression where delta f is equal to f sub s divided by big N. So we see that value as well. So things are working out pretty well so far. So let's see. Okay, so we've already calculated delta t. We've got delta f. We've got the Nyquist frequency. We've got the period. We've got the sampling frequency. We've got n. And let's just double check that we hit all those values. So we want to calculate those without even having to read the problem. So I've got my big N. I've got my delta t. I've got my S sub S, I've got my F Nyquist, I've got my period. What else? We've got everything? I'm pretty sure we do. We're amazing. We're going to be ready for this exam. So I already know what's my lowest frequency. That's going to be my delta F. That's going to be my lowest frequency. What's my maximum frequency? That's going to be my F Nyquist. And with that, I can kind of go ahead and solve out the rest of this problem. So I know that I'm only going to go through, if n equals 6, I'm going to have 3 harmonics. So because I always go to n divided by 2 number of harmonics from my discrete Fourier transform to my Nyquist frequency. So I'm going to have 3 harmonics. So and a sub 0 and b sub 0. I want to calculate this as well. So let's go ahead and kind of write out these values and let's calculate it. So I'm going to treat this function as, again, a Fourier series. So I'm going to go ahead and say that my, actually I don't even need to look at kind of my time data. So I just really need to kind of pull in my raw y values. So my y vals, or actually we'll call it my y vals equals 5 minus 7, 31, 31, minus 7, and then 5, and then repeat. 5 minus 7, 31, 31, et cetera, et cetera, et cetera, et cetera. So that is my periodic kind of function here. So now I need to kind of calculate my a sub n's. So remember, that was a little bit different than our discrete Fourier transform. So now we're going 2 divided by n times, now we need to kind of write our table function. So let's just kind of, again, remind ourselves a little bit of our discrete Fourier transform. So 2 over n, and we're pulling in essentially these values. So our r here is essentially these, data points. So what is my first data point? Y. What is my second data point? Y. What is et cetera, et cetera, et cetera, et cetera, et cetera. So I need to do a table where I simply just pull out basically my y vals I times cosine of 2 times pi times, actually we're going to call it, instead of I, we're going to use r. Cosine of 2 times pi times r times n divided by big N. And so first we're going to, before we kind of, deal with any harmonics, we have to kind of pull out and do the summation here. So we're doing a summation operation in this kind of expression. So we need to pull out all of the data points. Now remember, all of the data points once we define our period. So I'm going to go ahead and pull out r goes from 1 to length of y vals. There it is. And so now you see in this expression, this is n. So now this is just, we need to do a total here. So we need to do the sum. We're adding all these values. So there we go. We've got it. So we're now going to go and figure out this value. So I now need to do another table function, and now we're going to do it as a function of n. So n is going to go from, we could actually go from 0 to big N divided by 2. It's right here. And actually, let's go ahead and where is my, I have a little bit of an error in my code here. And I'm trying to see where, because you're going to go from 0, oh, where is this big, that's why you don't, big N. There we go. Now we're much better. So there's our a sub n's. Those are our b sub n's. What do you think the first coefficient is going to be there? So my b sub n's, only thing that changes is my sign, and b sub 0, 0. So that's a good double check. Everything's looking copacetic. So we can go ahead and now do very similar kind of plot. So I could do my c sub n equals table square root a sub n I squared plus b sub n I squared. And I'm going to go from I from, again, probably should be using n, but it's okay. I from 1 to length of a sub n. So my b sub n's going to be, or actually my freaks are going to be equals to table I times delta f. And I'm going to go from I from 0 to basically length of c sub n minus 1. There we go. So now I can transpose those, and actually I'm going to go ahead and steal the, again, it's not stealing because we wrote that code ourselves. That is our copyright Just kidding. Not really kidding. That is we did a lot of work to get those. And as we see here, let's see what the dominant frequency is. Let's pull back a little bit. It looks to be the third harmonic. Again, zeroth order harmonic we don't really care about, but the third, actually second harmonic, excuse me, second harmonic, 0, 1, 2. The second harmonic is our dominant frequency. So that looks pretty nice. I like it. So we're looking good so far. So let's see what else we have to do to kind of finish up this question. We left the exam, so now we know what our dominant frequency is. It's the second harmonic, so it's going to be that second frequency. Let me get rid of this guy. We don't need it. We don't need that one anymore. So if I want to look at so it'll be my freaks. Say the third value here, so 33.3. Maximum frequency, I already know that. And yeah, that's pretty much it. That's all this question asks for. So you've already aced it. So that's the question on the exam that's going to, I think people are going to do very well on. So now we're going to go move on to question 3, and you're already halfway through the exam. Congratulations. I'll see you in the next video.